This is part two of our final exam review for statics. And this is going to cover basically chapter 5. That was the primary content on your second midterm exam. Chapter 5 was all about rigid body equilibrium problems in both 2D and 3D. And every one of these problems has at its heart a first step of draw a free body diagram. And to do a free body diagram, you first remove all of the supports, and then you replace those with what they do to the object, right? They can either provide reaction forces or what we call reaction moments, or both. And the idea is that a reaction force is there whenever that support prevents translation in that direction. So if it prevents translation in the X direction, you have a reaction force in the X direction. If it prevents translation in the Y direction, there's a reaction force in the Y direction. Reaction moments arise when the support prevents rotation, and whatever axis it prevents rotation about gives rise to a reaction moment. We have these tables in our book for 2D and 3D, and I've got several of the most commonly used ones on your equation sheet, but it's useful to kind of review. When you have a cable or a weightless link, as shown here, you have just a single unknown, and that unknown is a force in the exact same direction as your cable. If you have a roller or a rocker, these are basically the exact same kind of connection, actually also a smooth contacting surface or a roller or pin in a smooth slot, or a collar on a smooth shaft. All of these, everyone from number 3 down through number 7, are treated exactly the same. They provide what's essentially a normal force. Only a normal force. Normal means perpendicular to the surface. So you'll notice in all of these pictures, you've got a force and there's a little perpendicular right angle indicating that force is perpendicular to the surface. Every one of these is exactly the same that way. They all have that force perpendicular to the surface, because since the surface is smooth or it's on wheels or a rocker, the idea is that the part is free to slide along the surface, so the support only prevents motion perpendicular to the surface. So everything so far only has a single unknown force. The only things that get more complicated here in 2D are this pins. You guys have seen lots of pins this semester. A pin is a very common support, and I like to draw my free body diagrams using pins in this first way, where you have an unknown force component in the X and an unknown force component in the Y direction. So that is how I do pins right there. We haven't used number 9 very often, but this is the idea of a kind of a rigid part attached to a smooth shaft. So the part can't move perpendicular to the shaft. That gives rise to this reaction force. But because of this kind of rigid bar-like attachment, it also, the shaft it's on prevents rotation, and that's why you would also have a reaction moment. The other really common one that we've seen a lot this semester is the fixed support. Here at the end is usually just shown like the bar dead ends into a wall. If I'm drawing this on paper, I typically draw it with these kind of slanted lines to make it look like it's totally clamped. It's not just a pin. So for a fixed support, I'm going to use this kind of a notation. It has 3 unknowns, a force in the X, a force in the Y, and then that clamp means that it also prevents rotation. And the way it prevents rotation is by providing a couple. So what it does is it provides a net force at the top and a net force at the bottom to prevent rotation. If this tended to want to rotate, say, down that direction, the wall prevents it. So we don't really want to find how big those individual forces are or how far apart they are. We just want their overall effect, and we capture that through this reaction moment. Now, in all of these, you often do not know the direction that the reaction forces or moment might act, so you simply guess. And then in the course of solving, if you get a negative sign, it means your guess was wrong and it actually acts in the opposite direction. 3 dimensions are a little more complicated, but not too bad. We still have several at the beginning that are just like in 2 dimensions. If we have a cable, if we have a smooth surface, roller, these are just like in 2D, where you have a single unknown force. Here we have a single normal force, another single normal force perpendicular to the surface. So those are all just the same as in 2 dimensions. Now we get to some of the new ones. For a ball and socket, this is a fairly common support. Ball and socket allows free rotation in every direction, but prevents translation in all 3 directions. So you end up with an Fx, Fz, and Fy. Then we have a series of bearings. So bearings are treated differently if they are used all by themselves as a single bearing versus as a pair of bearings. Oftentimes bearings come in pairs or more on a shaft. So here's the thing I want you to remember is that the couple moments are generally not applied if the body is supported elsewhere by another bearing. So with bearings, the idea is a journal bearing allows for free sliding along the length. So what a journal bearing does is it prevents motion perpendicular to it. And if it were by itself, it would also prevent rotation about this x-axis and about the z-axis, but it's intended to allow free rotation about the axis through its length. So by itself, it would have these 4 unknowns reactions, but if it's in a pair with another bearing, you would not include the moments. You would only include those 2 perpendicular forces. How is a square journal bearing different? The only difference with a square journal bearing, it has all the same features as a single journal bearing, but now because the shaft is square, it also prevents rotation about this axis. So we add on this my reaction moment. We also have bearings that are called thrust bearings. Usually we put a thrust bearing and a journal bearing together as a pair, where the journal bearing would allow translation along that axis. The thrust bearing is capable of providing force along its axis, so you're not free to slide through a thrust bearing. So what we add here, this is the same supports, same reactions as the journal bearing, but now we've also added this Fy for a thrust bearing. We haven't really used these single smooth pins or hinges. They're roughly the same idea as a thrust bearing, where if you have it in conjunction with another support, you're not going to include the moments. And so they end up actually acting in that case kind of like a ball and socket, where they just prevent translation in all of the directions. But our other very common support that we see in 3D is this fixed support here at the end. At a fixed support, the idea is you're preventing all possible motions in all directions. So you will have six unknowns when you're dealing with a fixed support, because you have Fx, Fy, and Fz and moments about the x, y, and z axis, because it prevents rotation about all axes. So those would be Fx, Fy, Fz, unknown reaction moment about the x-axis, y, and z. So what are the common mistakes that I see in these kind of problems? Sometimes you'll forget a 2-force member, right? 2-force member is anything that has a pin at both ends, typically, and nothing else acting on it. So a 2-force member has to have a force acting along its length. If you can recognize it's a 2-force member, you can remove it and you know the direction of the force. So you know the force direction. Too many reactions is another common mistake I see. Sometimes, usually this is because of not recognizing a 2-force member, or could mean that you saw something was a roller and you treated it like a pin. Treating a roller or rocker or a pin and slot like a pin support. So it's where you have a support that should only have 1 reaction force at it and you put 2 on there. You'll have too many reactions, you won't be able to solve it. Too few reactions is usually because you forgot a moment. So I see this like at a fixed support. If it's a fixed support, it needs a reaction moment. So make sure you include it. If it's not a fixed support, it doesn't need a reaction moment, so make sure you leave it out. This internal versus external forces actually matters more in the next set of slides when we're talking about trusses and frames and machines. But I do see this occasionally even in these chapter 5 questions with pulleys. So only include internal forces like the tension in a pulley or forces at a connecting pin if you cut the cable or break apart the structure, which we do more in the next chapter. All right, so what do our equilibrium equations look like in 2 dimensions for rigid body equilibrium? So this is no longer particle equilibrium. These parts actually have some dimension to them. We'll have 3 equations in 2D. We'll have the sum of the force in the x equals 0, sum of the force in the y equals 0, and the sum of moments about the z-axis through a point are equal to 0. So that means we can have a total of 3 equations. So we can solve for 3 unknowns. And it might be helpful before you solve a problem like this to write down all of your unknowns, count how many there are, and make sure you have enough equations. In 3D, we can have 6 equations. We can sum forces in the x, sum forces in the y, sum forces in the z, and we can sum moments about an x-axis, a y-axis, and a z-axis. So that's 6 equations and 6 unknowns. And it's a great check is, do your number of equations match your number of unknowns? If they don't, there's a very good chance that you've made a mistake. There are some 3D problems where you may end up with only 4 unknowns. And that usually is, an example might be if you've got a triangular plate with a downward weight and upward forces, T1, T2, and T3. That's a 3D problem with only 3 unknowns in it, but it turns out there are actually only 3 useful equations that you can write, because if you try to sum forces in, say, the x direction, there are no forces in the x direction, so you just get 0 equals 0. Try to sum forces in the y direction, there are no forces in the y direction, you get 0 equals 0. And if you try to sum moments about the z-axis, every force is directed in the z direction, so all of the moments equal 0. So 3 of your equations are not useful. So that's an example of a problem that's 3-dimensional where you can actually only solve for 3 unknowns. So it only has 3 unknowns. So what are common mistakes that I see is when summing moments, I see a lot of students using the wrong lengths in their moment equations. So you always want to be using perpendicular distances. If it's not a perpendicular distance, it's the wrong distance. The force components when summing moments are the other issue that I see a lot. So let's draw a little picture here. Let's say I have a beam, and here's point A that I want to sum moments about, and let's say that I have a force right here. And I want to sum the moment that causes about point A. Well, that force is oriented at an angle theta. And so I have a couple of options when summing moments, but what I think is simplest is to break the force into its components. So this will have an x component and a y component. And you're looking for perpendicular distances. So when I look at Fy, it does have a perpendicular distance back to point A. It's that length L. But when I look at Fx, it is directed right through point A. There is no perpendicular distance at all. So the moment that force causes about point A is going to equal the y component of the force times L. And it looks like that would end up being a counterclockwise moment. Your homework, but I want to draw what the free body diagram would look like. And typically, you don't want to draw your reactions directly on the pictures. You want to draw an actual separate diagram, but I'm going to draw these on the picture so that it's kind of quick. At B, it looks like it's sitting on a smooth surface. So you're going to have a force at B. You can call it the normal force at B if you want. It's going to be perpendicular to that surface. So we need to give it an angle. Here's my tip for angles. Well, if the surface is at a 5, 12, 13 angle, then this will be also at a 5, 12, 13, but we need to flip and put the 12 on the vertical side and the 5 on the horizontal side and the 13 right there. If that's a little too small to see, here's the vertical side, horizontal side. There's my normal force direction. The 5 goes here, 12 goes there, and the 13 is along the hypotenuse. Okay, that's a little trick that whenever you've got the slope of one of the lines here given by 5, 12, 13 triangle, the thing that's perpendicular to it will be the exact same triangle, but if the 5 was on the y side, now the 5 goes to the x side. And if the 12 was on the x side, the 12 goes on the y side. So smooth surface, single unknown, it's a normal force. Here over here at A is one of those funny collars, like a rigid collar on a smooth rod. So the idea here is that that collar is free to slide along the rod in this direction. So there's no force in this direction, but there will be a force perpendicular to it. So I'm going to draw that as, you can call it the normal force at A if you want. Same idea as before. If we have this little 3, 4, 5 triangle down here, this will also act on a 3, 4, 5 triangle, but I need to flip and put the 3 on the vertical side and the 4 on the horizontal side and the 5 along the angle. And then this is not just sitting on a smooth surface like it was at B. This is actually a rigid collar type shape. So this is going to prevent rotation as well. So you also, for this problem, would need to include a reaction moment at A and then go and solve for it. And it's a two-dimensional problem. And I just drew on here. Let's count them up. 1, 2, 3 unknown reactions. 2 are a force and 1 is a moment. So I should be able to write enough equations to solve. One mistake I've seen quite a bit in this semester is when people are looking at, say, this applied couple, 200-pound-foot couple. I've seen a lot of students try to include that somehow in their force equations. You don't want to do that. For this problem, when you sum forces in the x direction, you'll just have the 4/5 of NA and the 5/13 of NB. Those are your only x forces. In the y direction, you'd have 100 pounds. You'd have the 3/5 of NA upward and the 12/13 of NB upward. Those are your only forces in the y direction. And then when you go to sum moments, you'll need to pick a location to sum moments about. And let's pick point A to sum moments about. You would include in that equation your counterclockwise guess at MA. You'd include in the other direction your 200-pound-foot applied moment. The normal force at A causes no moment because it's sitting right at A. The 100-pound force, you just multiply it by the 3-foot perpendicular distance. And now NB, I don't know the perpendicular distance, but if I can split it up into a vertical component, 12/13, and a horizontal component, 5/13, the vertical component, I would use this long 6-foot distance as the perpendicular distance from point A. And the horizontal component, I would use this 2-foot distance from point A. And let's see, MA is counterclockwise. This is going to cause a clockwise moment. 200 is clockwise. The vertical component of NB appears to be counterclockwise, but the horizontal component of NB is clockwise. So figuring out the counterclockwise and clockwise so that when you sum them up, you put pluses and minuses in front of the right ones is going to be really crucial for solving this problem. The other 3 of my examples on here are 3-dimensional. So let's draw those free body diagrams, see what we need to go on them. So in the second one, at point A, we have a ball and socket. So at a ball and socket, it's free to rotate, so there are no reaction moments, but you will have a force in the X, Y, and Z directions, all 3 unknown reaction forces. And then I've got a bearing at B. A bearing, I'm told in the problem it's a journal bearing. So B is a journal bearing. So because it's a journal bearing, the shaft is free to slide through it, but it can't move perpendicular. So I'm going to end up with 2 perpendicular forces, a BZ and a BX. And because there's also another support in this problem, I'm going to not include the reaction moments. If this were the only support on the problem, I would need to include the reaction moments, but because there's another support, only include those forces. So counting this up, it looks like I have 6 unknowns. I've got my 3 unknown forces at the ball and socket, 2 unknown forces at that journal bearing, and then my unknown force P, because in the problem, we're told that this ball weighs 150 pounds, and we need to figure out how big of a P do we need to apply. So if all the problem asks is for you to find P, you can actually solve that with one equilibrium equation by simply summing moments about the y-axis. Can you see that? If I sum moments about the y-axis, all 3 of these forces and both of these unknown forces cause no moment. And I would simply have my downward weight of 150 pounds, which it looks like this radius is half a foot away, causing a moment about the positive y-axis. And then P looks like it is 1 foot down below. I want to use perpendicular distances. So from P to the y-axis, I just have to go straight up 1 foot. So I'd multiply P times 1 foot, and that's causing a moment about the negative y-axis. So we could solve that and get P directly. Then if we need to solve for the other forces, it's a matter of summing forces in the y direction. The only force in the y direction is AY, so that's going to be equal to 0. I like the idea of summing moments about the x-axis through point A, because if I do that, you'll notice that none of the forces at A cause any moment. Bx and P are both parallel to the x-axis and cause no moment. So all I would have is this downward force, 150 pounds, which has I guess it's a 2 foot distance back to the x-axis. And then BZ has got a 4 foot distance back to the x-axis. So I'd be able to figure out that 150 pounds times 2 feet has to equal BZ times 4 feet. Solve for BZ, then go back and sum forces in the z direction to solve for AZ. Then I'd probably sum moments about the z-axis through point A. None of these forces cause any moment about the z-axis because they go right through it. BZ and this ball do not cause any moment about the z-axis because those forces are in the z direction. So the only forces that cause a moment about the z-axis would be Bx, 4 feet away, and P, which I'd need to use 2 plus 2 plus 1 plus 1. It looks like it's 6 feet away from the z-axis in a perpendicular sense. That's the x distance. So I could solve for Bx and then go use my x-force equations to solve for Ax. Let's look at another one. I need to include the weight in this case because it's provided in the problem. Oh, I think I forgot to include that on this previous one. There should be a downward weight at that ball. I forgot to draw on there. Again, I have a ball and socket at A. So ball and socket gets AX, AY, and AZ. And then I'll have tensions in those 2 cables because I need to cut through the cables and remove them to actually draw a free body diagram. So I have a tension in cable BD and a tension in cable BC to solve for. And I think the weight is given in this problem. So we have 1, 2, 3, 4, 5 unknowns. The reason that we don't have a 6th unknown is look what happens if I try to sum moments about the y-axis. The y-axis goes right through all 5 of my unknown forces, and the weight is lined right up with the y-axis. So I'll get 0 equals 0. So there are actually only 5 equations that you can write for this problem. To solve it, I would first take TBD and TBC and write them as Cartesian vectors so that I can separate out their x, y, and z components. Let's do one of those just for some practice. Let's write down TBD as a Cartesian vector. Well, it has a magnitude that is unknown. And then inside of the vector, what I want to do is start at point B and go back to point D. And in doing that, I need to go in the negative x direction. It looks like 2 meters because I'm going from the y-axis back there. So I'd write down -2 in the I direction, 2 meters. In the y direction, to get from B all the way back to that plane that D is sitting in, I've got to go 1, 2. I'm going back 2 meters to get there, over 2 meters to get there, and then it looks like up 1 meter. So I have to go -2 in the j direction plus 1 in the k direction. Now I can't leave it like that because this is not a unit vector. To make it a unit vector, I need to divide by the square root of -2 meters squared plus -2 meters squared plus 1 meter squared. And if I've done my math right, that turns out to be square root of 9, which is 3. So this becomes TBD times -2/3 I -2/3 j plus 1/3 k. So that would be my first step, is getting both of those tensions into Cartesian vector form. Next, I probably want to start by summing moments to see if I can eliminate something fairly quickly. For example, I might take the x-axis through point A and then the z-axis through point A and sum moments. If I do that, if I'm taking the x-axis through point A, none of the forces at A contribute to the moment, but the weight will. And what I need is the perpendicular distance from the weight, which is out here, back to the x-axis. So its perpendicular distance would be 1 meter. And for these tensions, You may actually find it's easiest to write these out using a cross product in this case, because the tensions have fully all three I, J, and K components. Use a position vector that goes from A out to B. Write out your moment that each of these cause about point A. You do the cross product. What that would look like for TBD is something like this. So the moment about A for TBD would be I, J, and K across here. Your middle row becomes your position vector. It has to go from the point you're finding the moment about to a point along the force. So you could either use a position vector from A straight out to B, or you could go from A to D if you wanted. But A to B is simpler. That's just 2 meters in the Y direction. So I'd write this down as 0, 2 meters, 0. And then finally, your third row would be minus 2/3 TBD, minus 2/3 TBD, plus 1/3 TBD. And then we do that cross product. Okay, and what that will give us is how much of a moment TBD causes about the x-axis through point A, the y-axis, and the z-axis through point A. You can do the same thing for TBC to get its moment components about point A. Alternatively, you could look at this and say, well, TBD is going to have 3 components. Let me draw them. It's going to have a y component, an x component, and a z component. And you could say, if I'm summing moments about the x-axis, the y component won't cause a moment because it goes right through it. The x component won't cause a moment about it because it's parallel to it. So it's actually just the z component of TBD that'll cause a moment about point x. And the moment arm would be the perpendicular distance, which is 2 meters. And if you use the right-hand rule, starting here, going out and up, it's causing, your thumb would point toward the positive x-axis, causing a positive moment about the x-axis. You could do the same thing with TBC. It'll also turn out that only the z component will cause a moment about the x-axis. It'll also be positive. And the weight causes a negative moment because it's over here, down, going that direction. So then you repeat with the z-axis. Z-axis is actually a little bit simpler. For the z-axis, again, none of these forces cause any moment. The weight doesn't cause a moment about the z-axis because it's parallel to the z-axis. And if I look at my tension TBD again, you'll notice that, again, the y component goes right through the z-axis, causes no moment. The z component this time is parallel to the z-axis and causes no moment. So only the x component is going to cause a moment about the z-axis, and you'll come out 2 meters as your moment arm, times that component, and it's going to cause that sort of a rotation, which is a positive moment about the z-axis. And then TBC is going to do exactly the opposite because its x component is in this direction, so it's going to cause a negative moment about the z-axis. That's actually a convenient equation to use because you'll have only TBC and TBD in it as your 2 unknowns. Get one of them in terms of the other, substitute it into your other moment equation and solve for TBD and TBC. And then finally, use your force equations to solve for your other 3 unknowns. Okay, let's do one more free body diagram and we'll call it a good review for this part of the final exam. This one is going to have a downward weight, however much that thing weighs. It's got a tension in this cable, because to draw a free body diagram, we're going to have to cut that cable. And then I've got it kind of a funny looking support. You could think of it as kind of like a pair of bearings, but I want you to think of it more as just a whole overall support that's going to do a couple of things. You see how at point A, because of the nature of this support, it's attached to this little rod that fits, I think the problem says it fits loosely through these round bearings. So the whole idea behind this is the part's going to be able to rotate about the y-axis. But because of those supports, you wouldn't be able to move this left or right. You wouldn't be able to move it up or down, but I think you also wouldn't be able to move them left or right. So it appears to me, without any additional information, that this support is going to prevent motion in all 3 directions. So that means I'm going to put on here an AX, put on here an AY, and put on here an AZ. And then it also looks like it's going to prevent rotation about 2 of our axes. It's going to allow free rotation about the y-axis, but it should not allow rotation about the z-axis or the x-axis. So I'm going to call this MAZ and MAX. So I got 5 unknowns at that support because all that support allows is rotation about Y. So we need the other 5 of the potential 6 reactions in 3 dimensions. And then if I count up my unknowns here, I'm assuming that I know my weight. So I've got an unknown tension and then an AZ, AX, and AY. That's 3 more. And the 2 moments, I've got a total of 6 unknowns. So I will need probably all 6 equations to solve. And in doing that, what I'm likely to do if I'm solving this, I've discovered over time that summing moments usually helps you answer your questions fastest. So I am probably going to sum moments about the y-axis very first through point A. And the reason for that is the only axis that has no unknown reaction moment. And so if I sum moments about the y-axis, I will actually be able to solve for TCB in just one single equation. And then once I have that, I can sum forces in the x, y, and z to get AX, AY, and AZ. And then lastly, I'm going to go back and sum moments about the z-axis to find MAZ, and I'll sum moments about the x-axis to solve for MAX. So write out TCB as a Cartesian vector. Then I'm going to sum moments about the y-axis, the weight. I would use this 3-meter perpendicular distance, right? The weight's 3 meters away from the y-axis. For TCB, the z component will cause a negative moment about the y-axis, and it's 3 meters away. The y component of TCB will not cause a moment because it's parallel to y. And the x component, can you see that also will not cause a moment about the y-axis because it's directed directly at the y-axis, so the distance is 0. So my equation for summing moments about the y-axis equals 0 would end up being the weight times 3 meters minus TCB, not the whole thing, just the z component of it, also times 3 meters equals 0. And look at that. I've just solved for the z component of TCB. I can then use it to find all the other components of TCB. And then from there, sum the other forces in the other directions and sum the moments about the x and the z axis to get the rest of them. So that completes part 2 of our final exam review.